Hi, I'm Ishtiaq from University of California at Santa Barbara. Today I'm going to talk about how you can retrieve content from a web application without letting the service provider know what you are retrieving. This work was done in collaboration with D.V. Agarwal, Amar Labadi, and Chinav Gupta. We often query data from different applications where the data is produced and managed by the service provider. For example, a hedge fund may query about a stock ticker symbol to make business decisions. A person may look for resources on certain medical conditions, or we may want to learn about some very private and sensitive topic from a service like Wikipedia. Querying content from such public data repositories come with serious privacy concerns because the query content or the response retrieved may leak sensitive information. For example, if the service provider gets hacked by an external attacker or a rogue employee monitors queries of a particular client, they may know about the client's sensitive information such as business secrets, medical information, personal preferences, and so on. In order to prevent such privacy violations, both the user and the service provider may want to keep the queries hidden. The user may want to hide queries to keep their sensitive information private. On the other hand, the service provider may want to avoid fines and penalties due to undesired data breaches. In addition, there has been recent evidence of strong entities like nation-states or government agencies enforcing service providers to disclose user information. So if the server doesn't know the queries in the first place, they can avoid any such coercion and respect the privacy of their clients. So from all these, it is evident that hiding queries while retrieving content from a public server is critical for privacy. Now the question is, can a user privately query from a public data repository in the presence of a strong adversary who can compromise the service provider? The problem we just discussed can be modeled as private retrieval from a public key-value store, where an untrusted server has a key-value database and a client is interested in a particular key. The client constructs a query for the key and sends it to the server, and as response gets back the corresponding value if the key exists in the server's database. And the privacy goal is no one other than the client should learn anything about the key or the value. There has been a lot of research to address privacy in the database area. Most of this research on addressing privacy involves encrypting the data. However, these data encryption-based solutions are not applicable to the problem we are trying to solve. For example, there is a large body of work on encrypted database where a client encrypts their data and outsources it to the cloud. Another popular area of research is Oblivious RAM, where a client outsources encrypted data and also hides access pattern by shuffling the data. Both of these techniques are not applicable in our case as the data is owned by the server and the user cannot encrypt or manipulate the data. Now I am going to introduce our work Pantheon that provides a solution to the private retrieval from server-managed key-value store. Pantheon hides users' query even when the server or the entire communication infrastructure is compromised by an attacker. Performance-wise, Pantheon has 93 times lower latency from state-of-the-art and can support private retrieval from million-scale key-value stores with sub-second latency. Pantheon also has two more additional important features. First, it is a single round retrieval protocol in contrast with some prior solutions with multiple rounds, leading to some consistency issues. Second, Pantheon also addresses another limitation of prior works and support dynamic databases where the client's query is independent of the current state of the database. Pantheon aims to achieve both strong privacy and high performance, and designing a system like Pantheon comes with two major challenges. The first challenge is corresponding to privacy, that is to hide the query from the server and even then retrieve the value. The second challenge is keeping the retrieval latency low and improving the performance. Pantheon addresses the first challenge by composing two cryptographic building blocks named oblivious equality check and private information retrieval. And to address the second challenge, Pantheon uses a new efficient oblivious equality operator based on Fermat's Little theorem. Before we go into details of the first challenge, I will give a brief introduction of the two building blocks. First, oblivious equality check. Suppose an untrusted server holds a set of keys and a client wants to check whether a particular key exists at the server. This can be done using oblivious equality check. The client first encrypts her key in a specific way and sends it to the server. The server performs some computation between each key set and the encrypted client key and generates an array of encrypted values. The array contains an encryption of 1 where there is a match and encryption of 0 otherwise. Thus, the client obtains an encrypted selection vector, which only the client is able to decrypt. Next comes private information retrieval, or PIR. PIR allows a client to retrieve an element from a particular array location privately. Suppose an untrusted server has an array of n elements indexed from 0 to n-1, and the client wants to retrieve the element at a particular index. To retrieve it privately, the client first constructs a PIR query, which is an array of encrypted zeros and 1, an encryption of 1 only at the desired index, and encryption of zeros at all other places. The client sends the query to the server. The server performs some operation and produces a response, which is essentially an encryption of the element at the desired index. The server has no idea about the value hidden in the response. The client can decrypt the response and learn the value at the desired index. Now, composing these two building blocks, we can design a single round solution for private retrieval from public key value store. Suppose an untrusted server holds a key value database and the user wants to retrieve the value corresponding to a key privately. The user can first construct a query following the oblivious equality check protocol and send it to the server. The server proceeds in two stages. In the first stage, the server performs oblivious equality check with its keys and the client's encrypted key to generate an encrypted selection vector. Now, this encrypted output can readily be used as input for the second stage, where the server performs private information retrieval on the value set. And as PIR output, the server generates an encryption of the desired value, sends it to the client. The client can decrypt it and retrieve the value corresponding to her desired key. Using this composition, we could address the privacy challenge in a single round interaction between the user and the server. Out of the two stages at the server, oblivious equality check takes more than 90% of the total time and thus is a performance bottleneck. Therefore, to obtain low latency, Pantheon adopts a new efficient equality operator using Fermat's Little theorem. Let us now zoom into the oblivious equality check operation. Oblivious equality check can be performed using homomorphic encryption, where the client encrypts her desired key using homomorphic encryption and sends it to the server. Then the server performs certain homomorphic operations to generate the encrypted selection vector. Homomorphic encryption natively supports additions and multiplications over encrypted data. For example, using homomorphic addition, we can compute the encryption of the sum of two encrypted values without actually knowing the values. Similarly, using homomorphic multiplication, we can compute the product of two encrypted values. However, homomorphic encryption does not natively support comparison operations. For example, equality check. So, homomorphic equality check operations build upon using the addition and multiplication operations underneath. Existing homomorphic equality check operators are inefficient because they encrypt each bit of the operand separately and perform homomorphic operations on them. The best known homomorphic equality operator so far improves over this simple approach by applying several optimizations, but it still requires bitwise encryption and so suffer from performance and scalability issues. For instance, the best known equality operator requires more than 80 seconds to check equality between a 32-bit key from the client and 64,000 keys at the server. Pantheon addresses this issue by adopting a new homomorphic equality operator that operates in integer space. Essentially, checking the equality between two keys K1 and K2 implies checking whether their difference is 0 or not. And Fermat's Little theorem, which came up around 400 years ago, helps us to do this check in integer space. Fermat's Little theorem allows us to derive that if p is a prime number, then for any positive number a smaller than p, a raised to the power p minus 1 mod p equals 1. On the other hand, if a is 0, then a raised to the power p minus 1 is mod p is always equal to 0. So we can rewrite our equality operator using this expression for keys smaller than a predefined prime p, where we first take the difference of the keys, apply Fermat's Little theorem to distinguish between 0 and non-zero values, and then take one's complement of the value to obtain the equality in the desired format. Let us go through a quick example on the equality check operator. Suppose the server has a set of 4 keys and the client is interested in the key 12, which is encrypted. The server can perform oblivious equality check following 3 homomorphic steps. First, the server performs subtraction to get the difference, then performs some repeated homomorphic multiplication to raise the difference to the power p minus 1, and finally performs one more homomorphic subtraction to obtain the final oblivious equality result. This equality operator helps us reduce the number of costly homomorphic multiplications by a large factor and reduce the equality check time from 81 seconds to 1 second. Pantheon also uses some additional techniques to make it scalable. We use SIMD batching and a careful parameter selection to reduce costs for homomorphic operations. Then we parallelize individual homomorphic operations across multiple cores of a machine to obtain vertical scalability. We also deploy the Pantheon server over a cluster of machines to get horizontal scalability. Finally, we also propose a query compression technique to reduce the network overhead. Details of these techniques are available in our paper. To evaluate Pantheon's performance, we deploy it over Amazon EC2. We measure the latency to serve a query as the key evaluation metric. And as a baseline, we use the state-of-the-art work on constant wait keyword PIR that appeared in Usenix Security 2022. We measured latency for different database sizes and found that Pantheon has 93 times lower latency than the baseline. The distributed deployment of Pantheon can handle million-scale key value stores. For example, for 32-bit keys, Pantheon can serve a query from 2 million size database under 1 second. Now, to summarize, private retrieval from public data repositories is an underserved problem. Pantheon provides an end-to-end solution to this problem with its 2 key techniques, a composition of oblivious equality check and PIR, and reducing equality check latency using Fermat's Little theorem. Finally, Pantheon improves latency by 93 times over prior work. With this, I conclude. Thank you.